Alright, wait. So it has come to be. So I was offline, my God, for the last couple of hours. My computer decided to completely confuse me. Oh, wait, I'm not wearing my headset. I just ordered new headsets that will be coming in a few days. Oh my God, what a complete mess. What a complete mess. You're not going to believe what kind of mess I'm in with all the headsets. Oh my God, this is such a mess. Such a terrible, terrible mess. Anyway, but this mess was worthwhile because of this mess, I took a break. During the break, I was watching videos, and in one of the videos, there was this idea that gave me this idea how to finally have a very inexpensive. Wait, let me just make sure that the audio is good. Where is the audio? You're not gonna believe what kind of mess. Okay, let me see. Let me see. 1, 2, 3, 4, 5. You're not gonna believe what kind of mess. Okay. The audio is not in the right ears. The speaker is good. The audio is not in the right ears. The audio looks good. The speaker is what's going on now. The audio looks good. The audio. Okay, let's stop that. Let me see. Stop that. Everything looks okay. Very confused mentally. Something completely different. But that does not seem to be working. I'm not getting anything to my headphones for some reason. Let me try playing just any video. Let's just play this video.
This may seem like a rather bold assertion, but Bohr was hopeful that the exact mechanism explaining how this is possible would emerge
It's very
later.
quiet.
The third postulate introduced the idea
volume.
that the angular momentum of the electron is quantized in units of Planck's constant divided by 2 pi. And the final postulate suggested that photons of light are emitted by atoms whenever an electron moves from a higher energy orbit to a lower energy orbit. The justification of Bohr's postulates, or of any set of postulates, can only be found by comparing the predictions that can be derived from the postulates.
Okay, let's figure this out. So, okay. So there's 2 headsets. Speaker. Okay, this is the correct one. And the input is USB. Okay, this should be much better. Let's see if this works.
Mechanism explaining
1, 2, 3, 4, 5. Okay, this should be 1, 2, 3, 4, 5. Still very quiet.
Mechanism explaining
1, 2, 3, 4, 5. Still not going to the right place. 1 second. Still very quiet. Still not going to the right place. Still very quiet. Okay, earbuds.
with the result of the experiment. So we will now consider these ideas in a bit more detail. We will begin by looking at the...
What is going on? I don't know. Let's try this again. So the default... Oh, okay. No, that's the input. Okay. I see. The output is the headphone. Got it. Okay, that should be better. Slowly, we're working out all the glitches. Okay, so let's try. Oh my God. Okay, it's very loud. Okay. That glitch has been fixed. Okay, I think all the glitches are behind us. I think we're in good shape. Okay, that's done. And okay, we can
Quantization of
watch
angular
this now. 1 second. Let's. But we don't. I don't care about this. This is not why we're here. We're not here for that. We're actually here for me to explain. I'm here to explain a new design for the Michelson-Morley experiment to give us a non-null result. So we know that Michelson-Morley got a null result. For that, Michelson got the Nobel Prize, but he died being sure that his null result was incorrect, that he should have gotten a non-null result. And it seems like Einstein based his special theory of relativity on the null result. So we can, if we can show that Michelson-Morley properly done should give us a non-null result, then that is a violation of Einstein's theory of special relativity, which is always a good thing. So let us try to explain. So let me try and explain to you how we can reproduce Michelson-Morley successfully, meaning non-null result. How can we do it with, I wouldn't say at home, but even if you use a lab, until now every experiment that I came up with was was a little bit expensive. Hopefully this will give us a much less expensive, much less dangerous, because we were using gamma rays or X-rays, or we had to build a very big rig with thousands of mirrors, which I don't know, you need very high, I don't think you can get, we need to bounce back and forth a laser beam between 1,000 mirrors. I don't think that's doable because you lose focus. The mirrors are very imperfect. So my assumption is that it would not work. So a space-based interferometer, that's really expensive. Gamma ray and X-ray, those are very dangerous and expensive. And I don't know who has access to these things. Anyway, so today I came up with a simple solution, relatively simple, and it's based on fiber optics. So this is the fiber optics Michaelson interferometers okay, so enter. Okay, so let me explain to you the solution. Is a very good solution, very nice solution. You will hear this solution, you will know it is the truth. You will know, I guarantee it. I guarantee it. I guarantee it. I guarantee it. Guarantee it. Guarantee it. Do you guarantee it? Yes, I guarantee it. All right. Let us begin. It's really very simple. There's really not that much to say. It's very little to say. So the first thing we need for this solution, right? So what are we trying to do? So what we're trying to do is fire a laser or a light in this direction. Oh my God. In this direction. Whatever, right? Either a laser or just a light source. It's really very simple. Then we're going to have a half mirror, which is just a mirror, a perforated mirror. So half of the beam is going to go through, and half of the beam is going to get reflected like this. And then we're going to put a mirror over here, a full mirror over here, and a full mirror over here. And we're going to get the signal back. So the signal will go back and hit the mirror again. Wait a minute. If this is, I think it's not only a half mirror, it's a two-way half mirror in that case. So it will hit here and will go there, while this yellow light will hit the mirror and go back and go through and arrive at the detector. Okay, that's an interferometer. You place it horizontally, and you rotate it. And if there is ether moving, if the ether is moving relative to you, relative to this apparatus, so if the ether is moving, so let's say that the ether is moving this way for some reason. Let's assume the ether is blowing past us on the surface of the earth, wherever we happen to be. Let's say we are in Ohio, not Cincinnati. Where were they? Ohio, somewhere in Ohio. Maybe Cincinnati? No. Cincinnati, I don't know. The name of the town, some town in Ohio. So if this is the Earth, this is the upper hemisphere, this is continental US, they were over here somewhere. So let's say that the ether, for some peculiar reason, is blowing this way. Now, is it really blowing that way? Well, the Earth, if this is the north, What do we know about the Earth? It's rotating. As far as I know, it's rotating. So the sun rises from the east. This is the east. And this is the west. That means the Earth is rotating that way. That is the rotation of the Earth. It's like this. It's rotating this way. So it's actually obeying the right-hand rule. Surprise, motherfucker! Surprise, motherfucker! All right, so it's obeying the. Oh, how is our audio? I think we tested the audio. Well, we should test it again. I don't know. Is it good? It's pretty good. Not bad. Let me just let me ask Sinas to join us, at least textually. Please, why is he not joining us? It's Sunday. Please join me in the text chat on YouTube. All right, whatever. So let me just So does that make me an experimentalist? I think it makes me sort of an experiment. If I'm designing experiments, like I'm giving you every detail of the experiment, I would say I am like people who manage labs. I mean, they don't do the experiment; they just manage the lab. They get a guy do this, they get a guy to do that. So I think I qualify as an experimentalist. It is an honor to be an experimentalist. It is an honor to be an experimentalist. Very nice. Very nice. Absolutely very nice. It's always a good day when I come up with an experiment, with a new design. It's not a new experiment, it's a new design for a very old experiment that no one cares for. I don't know. I mean, this shows you the complete, I would say, bankruptcy of the science institution. Nevertheless. All right. So this is the experiment. So we said, oh come on. So what did we say? So the Earth seems to be obeying the right-hand rule in its rotation. Very nice. I think it's obeying it. Anyway. Which leads me to conclude that yes, the ether is actually blowing in that direction. Why? Because if the Earth is rotating that way, and in my assumption, the ether is gravity. That is my theory. And it happens to be Einstein's theory as well, but Einstein said it's not flowing. That's fine. He's wrong, I'm right. And this will prove this. This one single experiment will prove many things. So it's really an important experiment. Nevertheless, so the ether is gravity. It flows straight into Earth. It flows into Earth like a fluid. It's not like. It is a fluid that is flowing into Earth. Therefore, as the Earth is rotating from west to east, we should notice we are moving through these lines of flow. We're cutting through the flow of the ether. So if this is the Earth's surface, and I'm standing here, and the ether is flowing towards the ground, my calculations show it's about 11,000 meters per second. If I am moving, if the Earth is moving, my calculations are, I didn't do a calculation. I would say in Ohio, it's about 500 meters per second. And this is about 11,000 meters per second flow. That's the flow of the ether towards the center of the Earth. Then at 500 meters per second, that's a ratio of 500 to 10,000. So what is it? Well, 500 to 1,000 is 1/2. To 10,000 is that 5%? I think it's 5%. It's half. Is it? I think it's 5%. What's 5? What's 10? It's 10 over 5. No, it's 10. That's 10,000 over 5,000. It's 10,000 over. It's 10. It's 5%. So I'm moving 5 units to the right as 10 or 11 units are moving down. Anyway, the point is that as the Earth is rotating this way, because I'm in Ohio, the Earth is rotating to the right. So I should notice an ether wind. The effective ether wind would be 500 meters per second to the west. So I should be noticing this ether wind blowing past me at 500 meters per second. The question is, what kind of effect should it have on a 1 meter? Oh my God, I cannot talk. Let me just text the guy. I cannot talk now. Oh my God, I closed everything. Oh my God, I hope I'm able to log into my chat. Let me use my iPhone. 1 second. This is terrible. Well, this is terrible. Come on. By the time my iPhone logs in, my laptop will also be ready. Okay. Fine, my laptop is ready. 1 second. All right. All right. So. 1 second. All right. All right. So I'll be texting while I'm explaining. Anyway, so I did the calculations. We did the calculations together, and let's say a 1 meter radius arm, which is basically the Michelson-Morely experiment. 1 second. Okay. So it's a one. This is about. This is 1 meter. So when you look at Michaelson-Morely, that's about 1 meter. Okay, so So 1 meter to notice a 500 meter with respect to light speed, which is 300 million meters per second, that's not doable. I mean, you're going to rotate, you're not going to see a wavelength interference. We were hoping to do one single wavelength for every 90-degree rotation. So this is what we call let's say this entire thing is on a plate. It can rotate. So from here we want to rotate to here. That's 90 degrees. So I was hoping within 190 degrees to see a single wave, a full wavelength in the interference pattern. That's what I was hoping, but that's not doable with these numbers. So what we needed was a much, much longer arm, more like 1 kilometer, which is 1,000 times. So I don't remember the numbers anymore. For 1,000, like a 1 kilometer arm. Yeah, I think even a 300 meter arm we should start getting results. I don't remember the numbers anymore. We have to go through the numbers again. Either 300 or maybe 600 meters arm or 600 meter diameter. Anyway, these are very big numbers to get a sturdy yet rotating plate of an interferometer on the surface of the Earth. That's not doable. When you're looking for a wavelength which is half a micron, half a millionth of a meter. What is this? One second. All right. So it has come to pass. I have a solution. So I was watching this video. Which video? Well, let's look at the history. It's not relevant. I was watching many videos because my laptop decided to not function. So I was just watching any old videos in history, hysterectomy. So I was watching, what was I watching? I was watching, I don't remember. What was I watching? 1 second. All right. What was I watching? It was a video, not this. It was. Oh, which one? Which one? Was it this one? Yeah, probably this one. Probably this one. This is a good, very good.
Is like the Earth and the Moon. He knew.
It's about momentums. Like you would ask, like, why would I watch a video about conservation of momentum? Because I'm still confused. What is? I mean, is force equals F equals ma? Like, I'm still confused about that. Anyway, so I think this is when they showed a particle collider. Yeah, there it is. This is a particle collider. So they were showing it. Is this where I saw it? And they said that the speed of, I don't remember. I'm never going to figure it out. Anyway, I was watching a video and they were discussing the speed of light in a vacuum and compared to the speed of light in liquids and plastics and dielectrics. Anyway, and then I thought, wait, I can run the interferometer inside water, in a water bath to slow down light. That would be nice. But how much can I slow down light by? 50%? Even 80%? That's still not enough. That could be good. We should look into that as well. Let me check it. Let me check. By how much does light slow down in water? We can use water. We can even use glass. What's the number? Factor of 165. So for that could be very good. So we can run this experiment just inside glass. So just have a glass cube, or even a glass rod. Just have 2 glass rods and run the experiment. If it slows down by a factor of 165, a reduction of the speed of light by a factor of 1/6 was reported. Team led slowed a beam of light to about 17 meters per second, which is significantly slower than its vacuum speed. 17 meters per second. Wait a minute, that's also a very good solution. If you can slow down light so much, then you should also get amazing results. To provide more, how? General answer: the speed of light in glass is typically reduced by a few percent compared to the speed in a vacuum. For example, in fused silica glass, the refractive index is approximately 1.4, which means the speed of light is about 1.46 times slower. So how do you get it to 17 meters per second, which is significantly slower? Okay, based on the provided that light slows down in glass due to the interaction between the light wave and the material's molecular structure. The exact reduction in speed depends on the specific properties of the glass, but here are some reported values: 95 by 165, 98, 17 meters per second. How could you get it to be so slow? At 17 meters per second, then the 500 meters per second that we're moving through the ether we should get an interference pattern very readily. So how do you do that? That's also really a good solution. If I can just use, is this glass? It doesn't say it's glass. None of these. I don't know. To provide a more general answer, the speed of light in glass typically reduced. No apparent slowing down of light in glass is an effect of the wave nature of light, explained by Jesse Clare, physics undergraduate. What? The light wave itself still propagates at the speed of light, but its phase velocity may be affected by the material's properties' apparent slowdown. So if we can get light to slow down to these values, what do you mean 17 meters per second? I mean, that's much slower than 500 meters. So we're moving through the ether much faster. So tell me more about this. Maybe Wikipedia. Let's go to Wikipedia. Maybe that's where it's from. Oh my God. Why is it so automatic? Why can't you remember? Okay, let's drink more water before we kill ourselves completely. So, oh my God, I always overfill my glasses of water. Why am I so terrible when it comes to pouring water? Jesus. Why doesn't Jesus help me when I pour water? My God, the water tastes awful. Awful water. Oh my God, I'd rather kill myself. Okay, slow light. Slow light is the propagation of an optical pulse or other modulation of an optical carrier at a very low group velocity. Slow light occurs when a propagating pulse is substantially slowed by the interaction with the medium in which the propagation takes place. Group velocities below the speed of light in a vacuum, C, were known to be possible as far back as 1880, but could not be realized in a useful manner until 1991. Stephen Harris and collaborators demonstrated electromagnetically induced transparency in trapped strontium atoms. Reduction of the speed of light by a factor of 165. 165, let's say 100. So instead of 300 million, it's 3 million. That's nice, but that's still going to be very difficult to get a result for a 1 meter apparatus. Was reported 95. In 1998, Danish physicist Line Vestergaard Howe led a combined team from Harvard University and the Roland Institute for Science, which realized much lower group velocities of light. They succeeded in slowing a beam of light to about 17 meters per second. How? In 2004, researchers UC Berkeley first demonstrated slow light in a semiconductor with a group velocity 9.6 kilometers per second. Okay, that's 10,000 meters per second. I mean, these are good numbers, but 17? How do you get 17 meters per second? I don't get it. Howe and her colleagues. So, Howe got the 17, okay, later succeeded in stopping light completely and developed methods by which it can be stopped and later restarted. How? Her name is Howe. Maybe that's how. In 2005, IBM created a microchip that can slow light fashioned out of fairly standard materials, potentially paving the way toward commercial adoption. Background. When light propagates through a material, it travels slower than the vacuum speed, c. This is a change in the phase velocity of the light and is manifested in physical effects such as refraction. This reduction in speed is quantified by the ratio. Okay, let's watch YouTube. Let's see if there is a YouTube video that shows this, that demonstrates this. Okay. Slow light. Slow light. Slow light. Solving the slow light paradox. It's a paradox.
I have two arrows here face the same direction, but not really. They're actually facing the opposite direction. Now, I've been told that refraction happens because light moves slower in water than in air. So it's like a tank driving that suddenly hits some mud at an angle. This causes it to turn into the slower moving mud a little bit. Now, this explanation makes sense, but did you hear what I said? The speed of light slows down in water. The most famous constant in the universe, the speed of light, named after the speed of light, slows down. Now, that's what I've been told my whole life, but I'm not going to take their word for it anymore. I'm going to actually try to measure it. In 2001, Professor Line Howe from Harvard achieved something seemingly impossible. She and her team shined a light in a supercooled material. The light in that material slowed down from 300 million meters per second to just 17 meters per second. And eventually they were even able to stop the light completely and then start it up again. But what does this even mean? Does light actually slow down in different materials, or is it just a trick? Luckily, we live in an age where we can easily get our hands on an instrument where we can measure the speed of light. So let's check if it's always the same using a technology called time-of-flight LiDAR. On the back of an iPhone, there's an array of infrared lasers right here. You can't see these infrared lights with your eyes, but the camera sensor can pick up some infrared lights.
1 second, I missed.
So let's check if it's always the same and different, then start it up again. But what does this even mean? Does light actually slow down in different materials, or is it just a trick? Luckily, we live in an age where we can easily get our hands on an instrument where we can measure the speed of light. So let's check if it's always the same using a technology called time-of-flight LiDAR. On the back of an iPhone, there's an array of infrared lasers right here. You can't see these infrared lights with your eyes, but the camera sensor can pick up some infrared light, so you can see it blinking here. In fact, if I just use a night vision camera, then you can see the laser array shining from my phone. The phone can actually use these infrared lasers to measure how far away something is. It sends out a short pulse in the nanosecond range of light, and then measures how long it takes to see the reflection of that light. Now, since light moves really fast, that reflection happens very fast. The phone can actually measure that slight delay in time. So to get the distance, you just take the time delay times the speed of light constant divided by 2, since it has to go there and back. Now, you can download apps that can show you the distance of things in front of the camera using LiDAR. But the key here is that the distance that the app is outputting is based on the fact that the speed of light is constant. If the speed of light changes, then the distance will be incorrect. So let's see if the distance changes if the light has to pass through a different material. So right now I'm going to focus this Action Lab sticker here. Then I'll take this acrylic block and move it in front of the camera. So it's still focused on the sticker, and the infrared lasers are going right through the acrylic block. But notice how the distance changed.
20.
So it actually changes from 17 centimeters to 20 centimeters. Now, even if you thought it was just because we're putting something in front of it, that still doesn't make sense because this is actually a shorter distance, so the distance should decrease. So we know it actually is measuring below to the sticker.
So it's
the only thing
down.
that could mean is if the light was actually traveling slower through this acrylic block. Now, this change wasn't that significant, so let's try to make it more significant by using a much longer block of acrylic. I'll use the wall of my vacuum chamber here. I can still focus on the sticker shining through the whole length of the acrylic. First, when I just focus the sticker through the air, it gives me about 54.2 centimeters. But now when I do it through the acrylic, it gives me about 82 centimeters. That's a huge difference. So it would seem that the speed of light has actually slowed down significantly. In fact, I can calculate
30%.
how much it has slowed down using the incorrect distance. The new speed of light is just the true distance divided by the incorrect distance times the actual speed of light. So if I just take 54.2 divided by 82, then I get the speed of light through the acrylic is only 66% of the actual speed of light. And I can verify this by looking up the refractive index of acrylic, which is 1.5. The refractive index is just the true speed of light divided by the speed of light in the material in question. So that's exactly what I measure. 1 divided by 1.5 is 67%. We can stick any other transparent material in front and get the same results. So we've actually directly measured that the speed of light does slow down in different materials using the time of flight LiDAR. But there's a problem. Light has no mass. And according to Einstein's special theory of relativity, anything that has no mass must travel at the speed of light. But if light always travels at the speed of light, then why can we measure it being slower than the speed of light in this experiment here? Well, first let's define what we mean by the speed of light. Let's take a wavelength of light passing between two objects. The speed of light can be found by just choosing one peak of the electromagnetic wave and seeing how long it takes to travel between the two objects. Now, this speed is always constant. It is the speed of light, regardless of the frequency of the light. The peaks always propagate at exactly 299,792,458 meters per second. So all light moves at that speed. But we don't always see it that way when there are other charged particles near. For example, let's say that we shine our light through a material like this acrylic. Since it's made of atoms, the atoms have electrons that are affected by this changing electromagnetic field. When the light hits the electrons, they start to jiggle up and down in the jiggling electromagnetic field. And when a charged particle jiggles, it now sends out another electromagnetic wave. These two waves both move at the speed of light, but they combine together to give some third wave that's a combination of them both. This third wave still moves at the speed of light as well. So far, it's not clear how or why any light would appear to be moving slower. But that's because we've only showed one electron. In a real material, if we take a slice of it, then it would be like we have a line or a slice of electrons. These electrons wiggling up and down can be modeled as a charge held in place by little springs. Now, if we model it in this way, then we find that the electric field just outside the plate of charges is equal to a constant times the derivative of the electric field of the light shining on it. So our light hitting the electrons is just a wave, which would be modeled by some constant times a cosine function. So that means that the electric field produced by the moving electrons is the derivative of the cosine.
Okay, I'm lost. As soon as he showed this model, I didn't understand how the model works. And I don't know if I care right now how it's putting me to sleep. I don't know if I care why light slows down. I just want to know how she slowed down light to basically to stop it. How do you stop light? And if it's doable, then let's build an experiment based on that. I don't care right now to understand the theory of slowing down light. I don't care. I don't care. And it's putting me to sleep. I don't like it when videos put me to sleep. Wait, we have a video from one of my favorite beautiful girls. Oh my god. Oh my god. This is not good news. Not good news. Not good news. Not good news at all. Very nice. Very nice. Wow. Some chicks are just unbelievable. So beautiful. So beautiful. So beautiful. Very nice. Very nice. Okay, let's continue. So I don't know if I care right now about this. So I just tell me how she did it, please.
We've only showed one electron. In a real material, if we take a slice of it, then it would be like we have a line or a slice of electrons. These electrons wiggling up and down can be modeled as a charge held in place by little springs. Now, if we model it in this way, then we find that the electric field just outside the plate of charges is equal to a constant times the derivative of the electric.
What is this? Whoa. What is this? E sheet is proportional to a negative constant times the derivative of the electric field. What?
Field of the light shining on it. So our is equal to a constant times the derivative of the electric field just outside the plate of charges is equal to a
just outside the plate of charges. What is he talking about? Oh my god. This is why people hate math. It's not like I don't know math. I hate it when they just here's the equation, like no derivation, no explanation, nothing. This is why people hate math. It's not that people hate math. People hate it when you just dump a mathematical equation with zero explanation. 1 second. Message. Oh, I should take this call. I definitely should take this call. Okay, so let's maybe end it. Maybe I'll continue next time. I'm falling asleep either way. How long have we been streaming? We've been streaming for 47 minutes. It's okay. Okay, we're gonna stop here. We're gonna stop here and kill ourselves. See you next time.